All right, so let's take a look at a couple examples on analyzing a parallel network or circuit. So thus far, we've learned how to identify parallel components, and we also learned how to add parallel resistors. So let's take those two tools, put them in our toolbox, and let's apply them. All right, so this one right here says determine Vs, which is the source voltage, IT, which is the total current, RT, which is the total resistance or total equivalent resistance, the total power, the current through resistor 1, current through resistor 2, and the power delivered or absorbed by resistor 1, and the power absorbed by resistor 2. So let's take a look at this one. So, all right, so I'm just thinking, what's the best way to approach this one? All right, so VS, that's an easy one. That was already given. So this is your source voltage right here. So that's going to equal 12 volts. All right, so now I total. So I total is going to equal VS over R total. So I total is right here. This is the current that's being supplied by the voltage source. All right, so we have VS, a voltage source, but we don't know what R total is. And so for this one right here, I'm going to use a simple equation. So R total equals 1 R1 times R2 divided by R1 plus R2, which equals 1 kilo ohm times 3.5 kilo ohm divided by 1 kilo ohms plus 3.5 kilo ohms. All right. And so go ahead and multiply that out. Plug it into our calculator. You got 1, 3 times 3.5 e to 3 divided by 1 e to 3 plus 3.5 e to 3. All right, and so we get 777.78 ohms. All right, so that's our total. So far we found this one, and we found this one. So that's our total. And so now we can plug our total back into this equation right here to find I total. So we got VS, which is 12 volts divided by 777.78 ohms. And so, and pull the calculator back up. And we get 12 divided by 777.78. And what we get is 15.43 milliamps. All right, so we found I total. All right, so we could calculate P total. Let's do that next. So P total is going to equal your source voltage or your total voltage, however you want to call it, times your total current. And so when you plug those two values in, you get 12 volts times your I total, which is 15.43 milliamps. And so let's calculate that one. 12 volts times, go up and grab that. You get 185.16 milliwatts. All right, so we got that one. And now let's calculate the current through R1 and R2. I think I may run out of some room, but let me see if I can get it all to fit. All right, so I1, trying to find I1 right here. This is I1. This one over here is I2. All right, so we're trying to find the current. What we need is we need the voltage and we need the resistance. And so we have the resistance and do we know the voltage? We do, because the voltage across a parallel component is always the same. So as you can see, R1 is in parallel with the source voltage. So therefore the voltage across R1 is going to be 12 volts. So whatever component or resistors that are in parallel, they're going to have the same voltage. So not always are parallel resistors voltage is going to be the same as the source voltage. As we get deeper into series and parallel networks, you'll learn that the source voltage is not always going to equal to the parallel voltage across each resistor. What I'm trying to say is that the voltage across parallel components is the same. Okay, in this particular example, the voltage that's in parallel with R1 is the voltage source. So therefore, we can call this V1 divided by R1. And so V1, the voltage across R1 is going to equal 12 volts. So actually, what's the voltage across R1? You can easily just look at this circuit and say, well, it's 12 volts. All right, so what is R1? 1 kilo ohm. And we put into our calculator, we get 12 divided by 1 to the 3, which is 12 milliamps. All right, so what about I2? All right, so I2, we're going to need V2 over R2. But what is V2? The voltage across R2. Well, same thing as V1. I mean, there's the voltage across, since these components are in parallel, they're going to share the same voltage. And so in this case, it's going to be 12 volts. 12 volts divided by R2, which is 3.5 kilo ohms. And so let's see what that equals. 12 divided by 3.5 kilo. and you get 3.43 milliamps. All right, so one unique thing about this type of circuit right here that I want to point out is that I total is called I total because it's the total current that's being supplied to the circuit. It's the highest current value that you're going to have in the circuit. That's I total. But if you look at it, I total is equal to I1 plus I2. So if you add up I1 and I2, you're going to get your total current. So as you can see, this is 12 milliamps plus 3.43 milliamps equals 15.43 milliamps. All right, so the way this thing works is you got 15.43 milliamps that's being supplied from the voltage source. It comes to this junction point right here. Some of it goes this way, some of it goes this way. And so for this one right here, for I1, we get 12 milliamps. Majority of the amperage is going through R1. And then a smaller portion is going through R2. But why is that? Well, current always follows the path of the least resistance. You're always going to have some current flowing in different directions, but majority of the current is going to flow in the path of the least resistance. And so in this case right here, the least resistance is 1 kilo ohm. All right. So it only makes sense for majority of the current to flow through this 1 kilo ohm resistance. And so as the current comes down to this junction point right here, it meets back up with the current that decided to go through this way. And this current is essentially I total as well. And then the cycle continues on and on and on. But that's another point that I wanted you all to remember, that current flows in the path of the least resistance. Okay. All right. So the last thing that we need to calculate is P1. All right. So P1, we know we need the voltage and we need the current. So V1, V2. All right. So do we have V1? Well, V1, what's the voltage across this resistor? 12 volts. All right. Do we have I1? We do. We just calculated 12 milliamps. And so we plug that in. 12 times 12 e to the minus 3 equals 144 milliwatts. And then P2 equals V2 times I2. And so that V2 is 12 volts times 3.43 milliamps. And so we plug that in to our calculator. We get 12 times 3.43 e to the minus 3. And then you get 41.16 milliwatts. And so, just like the current, if you add these two powers, P2 and P1 together, you'll get P total, just right here. So therefore, we found everything that we needed to find. And so these are different tools that you need to have in your toolbox in order to solve a circuit like this. Because not always are you going to have all the values. I mean, this one was easy because I gave you everything that you need to